chapter 14, section, is this 6? Okay, we're going to talk about directional derivatives and the gradient vector. I'm going to do notation a little bit differently than your book does because I think there's an advantage here. Here we go. F of x, x comma y. We know what that means. What's that mean, guys? Yep. PJ, you got me for 15 minutes more or no? All right, cool. We're going to do the limit as h goes to 0 since it's the partial derivative, right? This is the partial derivative with respect to x. That means in my difference quotient, where does the h go? With the x, yeah. F of x plus h comma y minus f of xy all over h. Right? Now there's another notation that your book does not use, but I think it's kind of cool. I'm going to let vector x be the vector x comma y. Your book doesn't do that. But if I do that, I have a new notation now. Or a new way to write this. I can say fx of vector x, and I just think that's kind of cool. Right? Anytime it says xy, well, only if you're comfortable with the idea that vectors and points are basically the same thing. They're ordered pairs. But if you're comfortable with that, then this is kind of cool. I can write this as the limit as h goes to 0 of instead of writing f of xy, I'm going to write f of vector x. See? And then what I'm going to write here is f of vector x plus h times vector I, because I means in the x direction. It's the unit vector. And similarly, if I want to do fy of vector x, that's the limit as h goes to 0 of, I'm going to subtract f of vector x again. What am I going to put here, guys? F of vector x plus h times vector j. That's right. So knowing about our unit vectors makes things kind of cool, because now what I can do is I can give you a definition that's equivalent to what the book does, but maybe a little more meaningful. The directional derivative. This is what Kathy was asking about. What if you're pointed in the direction, not in the x direction or the y direction, but somewhere else? The directional derivative of the function f I'll say at the point, and I'm going to say x, vector x again, because I like points to be vectors, in the direction of the unit vector u is given by, and here's the formula, you'll see a big D, you'll see a U here, of of f of, now your book is going to write xy, but I'm going to write vector x again. And that's equal to the limit as h approaches 0 of f of vector x plus h vector u minus f of x all over h. And while I have a really nice example that I do not have time to do, not with the way today went, guys. I'll zoom in for just a second in case you want to peek at it. I'm imagining temperature being represented by x squared plus y squared. Does that make any sense? Probably not. Because then the temperature at the origin is 0. The temperature at the unit circle is 1. It's like it's getting hotter as it goes out. So is this like anti-temperature? I don't know. But I computed the temperature. Oh, what I did was I computed the change of this function at the point 3, 4 in the direction making an angle of pi over 3 radians with the x-axis. So instead of being the derivative with the x-axis, it's like going at 30 degrees. I don't have time to do this, but I computed it, and I got 3 plus 4 radical 3. But what I do have time to do is show you how. How do you compute these things for real? Because you guys know in calculus class, we don't use this thing very often, unless we have to, right? And so I want to at least give you that going home today, the answer to how you do these computations. The gradient, the directional derivatives, we'll do the gradient vector on Monday, guys, because we're just behind. And they have nice pictures, but I want to show you this. How to compute the directional derivative. Okay? So, the theorem is this. Theorem. If f is differentiable at x, vector x, and vector u is a unit vector, then the directional derivative in the direction of u exists and is given by the following formula. What it's going to equal is the partial of f with respect to x, comma, the partial of f with respect to y, dot u. This thing has a name. This vector is called the gradient vector. And so another way to say it, you'll see this written. Grad f dot u. Okay, you'll see it written this way. Sometimes with an x here. Okay, so again, I'll finish with a closing of an example, and then we'll be done. T of xy, remember I said was, yeah, it's not temperature, I don't know what it is. X squared plus y squared. Okay? And what I want to compute, oh, I guess I need to tell you what u is. Well, okay, I said in the direction of 3 comma 4, but we have a problem. 3 comma 4, guys, is not a unit vector, right? So what do? I'm going to set u equal to, well, it has a length of 5, right? It has a length of 5, so if we divide by 5, that's my unit vector. Okay? Next, I'll compute the gradient of t. It's a vector whose x-coordinate is the partial derivative with respect to x. By the way, this is a simple example. What's the partial derivative with respect to x? And the partial derivative with respect to y is 2y. So what I'm telling you we're going to do is we can do du of t of x would be 2x comma 2y dot 3/5 comma 4/5. So what's that give me? 6/5 x, right? 6/5 x comma 8/5 y. Oh, plus 8/5 y, thank you. Plus 8/5 y. And so you could then compute anything you want. You'd have the directional derivatives given by this formula. All right, we'll do more next time, guys.
Just start by talking about schedule details a little bit. That's not it. Here's you guys. Yeah, here's your Blackboard page. Here's your schedule. Okay. So if you look at where I am, let me do this. Well, this is today, right? So today is February 20th. And yeah, I'm supposed to cover tangent planes and linear approximation. This is what I'm getting. But like I said, I really think that's the second half of today's lesson. The first half being the directional derivatives. I still want to do more with that, and gradients. Okay? That's kind of where I'm leaning. And then I just wanted to show you guys kind of looking ahead where we're at. So you'll notice that there's no homework yet for Wednesday. That will change. Okay, I'll update that. And so a week from today, I'm asking you guys to submit your project proposal. And the reason I'm doing that is I want to give you guys basically a month for this thing. And people have asked me, well, what exactly is this? And you'll notice that at the back of each chapter, it's only just kind of show you in the book. I don't know, pick a chapter here. Here's 14.1. So let me go to 13.9, which is fair game. And you'll notice that they list 5 different topics: designing a trajectory, intercepting a UFO, Cordic algorithms, how your calculator works. Love that. Bezier curves, love that too. Kepler's laws, okay. And I don't know if any of these topics catch your interest, okay. But if they do, the book comes with some really cool guided projects. And people that have had me for Calc 1 or Calc 2 would know about this already, okay. But basically, you should picture, what do these look like? Well, here's guided project. So there's about 20 questions, right? I think of it as maybe 2 to 3, depending on the project and depending on what you think. Here's one with 17. 2 to 3 homework assignments worth of material. I would say 2 because that's about how many questions are on it, but I say 3 because it's something that you're studying, not something that everybody's studying, okay? And you have about a month to work them out. That's really what we're at. Matter of fact, I should look on that calendar. When exactly is the due date for the project? I wrote down, let's see, so we're going to take exam 2 before break. We have spring break. Yeah, I said the end of March. So I wrote down Wednesday, March 29th, giving us about a month to get it done. Actually, you could do it over spring break, I guess, if you really wanted. I don't want that. I want you to do it when you want it. So I want to give you guys enough time that you can work on these things. And you'll notice we'll be into the middle of chapter 15 when it's due. Okay? And I think that chapter 15, again, is one of the... I think chapters 14 and 15, by the time you get into those, I feel like you're starting to figure out Calc 3. And so this is kind of a good time to get a project done. And I don't want to wait towards the end when you have finals and papers and all that other stuff. So that's kind of where we're at. All right. It's not a huge portion of your grade. It's 30 points. Okay. It's a lot more than a homework assignment, but a lot less than an exam. But my idea is it's a chance for you to study something you're interested in. You do not have to do a guided project. You can create your own project in conjunction with me, and I'll help you do that. And some of us have already been talking about that. Okay, so keep that in mind also. But the time to start the conversation is now. All right. Any questions? Okay. So let's get back to the directional derivatives we were talking about last time, right? So I wrote them this way as a shorthand, but basically what you're doing is we have already defined this and this, moving in the x direction and moving in the y direction. We have these things called partial derivatives. And this is how you did it, right, with the difference quotient. Either here with the h, or if you're moving in the y direction, you put the h by the y. So then the question is, can you move in any other direction and talk about that rate of change? And the answer is yes, and we call that the directional derivative. Okay? And then we said, well, how do you compute directional derivatives? Because we certainly don't like using the difference quotient. We do it as a last resort, right? We want to know how, but that's not typically what we do. And so there was this theorem that we showed that, oh, did I prove it? No, maybe I just used it for you guys. I said that if f is differentiable and you have any unit vector, then the derivative exists and is given by this formula. You can dot the unit vector with something that's called the gradient vector. This is a really important idea, this vector. The gradient vector is the vector of partial derivatives. So that's kind of interesting. And so we did an example. We said, okay, if this is my function, x squared plus y squared, and I want to move in the direction of 3, 4, I need a unit vector, first of all. So we made it 3/5, 4/5. And we took the gradient vector. Gradient of t would be this. That's pretty simple. And then we computed the dot product. So this was the idea. Okay. Yeah, I guess I didn't really show you why this works. So maybe I should do that. Why is it that this gradient vector dotted with that gives me the difference quotient? So what I did last time was fine. I just want to show you guys, look at the definition that your book gives of directional derivative. Now, is that the same as mine or not? I guess one difference is that instead of writing u as a unit vector, what did they write? They wrote h cosine theta and h sine theta. Now, let's think for a minute what that means. If I go back to what we wrote down, when we did the x partial derivative, we wrote x plus hi, I being what? Yeah, so what vector is I? I guess it would be 1, 0 if we're in R2, right? Or over here, J would be what? 0, 1. So that's the cosine and sine of pi over 2. And so the point is, we know that, these are kind of my extreme cases. If I want to have a unit vector, I want to be somewhere on the unit circle, right? And I know that whatever my theta is, this is the cosine of theta and the sine of theta. And so when your book says, all right, let's write it that way, that works out pretty nicely. So I guess that's kind of your answer to quick check 1. Pi over 2, of course, the sine of pi over 2 is 1. And then when they get down here, they say the directional derivative, okay, you can write as fxab and fyab times u1 dot u2, that unit vector, and times being the dot product. And the reason is the chain rule. Yeah, I think this is better than what I was going to write down, because we're just sticking to 2 dimensions, okay? So we're going to parameterize x equals a plus su1 and y equals b plus su2. And so this is kind of nice. Yeah, let's do it. Let's write it down. Sometimes writing it down helps. So again, I have a function of x and y, but we're saying that x is s plus, or a plus su1, and y is b plus su2. And so what I'm going to do here is I'm going to compute this. The directional derivative in the u direction at AB. That's what I'm going to compute. Kind of like, so we have already computed on the homework, you guys did this kind of thing. Fx of AB or Fy of AB, right? So we've already computed partial derivatives. Now we have this new kind of derivative. We want to go in the direction of u, and u is a unit vector, which we're saying is u1, u2. And I guess what I'll say is that the length of u is equal to 1. That's what we're saying. So we want to compute derivatives, so we're going to do the chain rule. And so here we go. They say, let's define the function g of s. Okay? And g of s is going to be what you get when you take f and you throw in a plus su1 and b plus su2. Right? So we're basically taking the function f. What is this? This is a Calc 2, a Calc 3 function, because it's a function of 2 variables. But since x and y are both functions of s, we're saying, we can rewrite that as just g of s. Okay? And so now I'm going to take the derivative of s. g prime of s. And then I'll compute g prime of 0 next. Why? Well, we'll see that shortly. So first let's do this. How do we do g prime of s? Well, we have to do the chain rule. Okay? So when we take the derivative of g with respect to s, and that's what they get here, they write df dx, okay? Partial of f with respect to x times, since x is a function of s, we can say dx ds plus partial of f with respect to y times dy ds. Does this make sense? Now what do we know about dx ds? I guess looking at the function, what's the derivative of this with respect to s? That's just u1. And what's the derivative of y with respect to s? That's u2, because these are constants a and b. S is my variable, right? So that's just a linear function, so that goes away. And so I guess what I have now is I have df dx times u1 plus df dy times u2. Oh, but wait a minute. I put a 0 there, so I have to be careful now, right? In order to put a 0 there, well, let's keep the s there for now, and then we'll come back to the 0. So these are functions of AB. So I guess what you notice then is that there's an easier way to write this, okay? The easier way to write what we have is this: gradient of f dot u. Okay? I guess throwing the 0 in is the same as if you throw a 0 in for s, then you're evaluating the function at a and b. I guess that's kind of what I'm saying, right? Because if you throw a 0 in for s, then x is a and y is b. All right. Picture. Graph the surface and interpret the yeah, this is actually a nice picture in the book. Let's see this. So here's a function that's more complicated than the one we did. I'm not going to go through all the derivative calculations because you guys could do that. Part A, when it says find the directional derivatives in the directions of u and v, you definitely want to do dot products. And so you're going to see that they do that. They compute some partial derivatives. Here's the dot products that they do. Okay? But my reason for showing the example is to show you the picture. So here is the surface. Z is a quarter, x squared plus 2y squared plus 2. Okay? And so now the question is, what happens if we compute the partial derivative in the direction of u? Okay? U here is 3 comma 2. Let me make this a little bit bigger. You guys see that? So we're getting the slope of this tangent line. If we're going to do the direction of v, so v is a different vector, right? V is pointed, it says 1/2 negative radical 3 over 2. So notice, at the same exact point, we're talking about very different tangent lines. You guys see that? but it's dot product of some unit vector down here in the xy plane with the gradient vector. The gradient vector being the partial derivative, so basically df dx and df dy. So here's the thing, guys. Why do we care so much about the partial derivatives? I guess the answer is because any rate of change you might possibly want to compute, you can get it very easily using a dot product with that gradient vector. So the gradient vector, there's one reason the gradient vector is important. But there's another reason that maybe it's even more important, okay? And that's what we get at next. So suppose you're on this surface, right? And you put a ball here. And you ask, where's the ball going to roll? Okay, well, answer is we know it's going to end up there, right? But what's the path it's going to take? I mean, is it like this? Maybe more so. Well, the answer is it's going to take the path of steepest descent, right? And we'd like to know what that direction is. Okay? And so there's another theorem that comes into play that has to do with the gradient vector. And so here it is. We called this thing the gradient. I already told you that. But I need the theorem. Here we go. That's the argument. Here's the theorem. The gradient points in the direction of steepest descent on the surface. Always. Why is that? Or another way to say it, here, let me word it this way. Theorem. A theorem is something we can prove. We being the world, not necessarily you and I. All right? But this one we can do. The theorem is the maximum value of derivative, the directional derivative of f is obtained in the direction of the gradient. And here's our proof. Let's let theta be the angle between my unit vector u and my gradient vector grad f, okay? So again, f is a function. When you put this symbol in front of it, you're getting the gradient vector. What is the gradient vector again? This means vector which is what? Yep. Comma. Yep. You know, but if I wanted to be 3 dimensions, right, I would go comma, and then I would go partial derivative with respect to z. And you can do that, and we will do that. Matter of fact, let me point out, the book does this, which I'm very happy about. After this discussion, you'll notice they don't leave this section without, they talk about level curves again. We'll come back to that in a second. And then they say the gradient in 3 dimensions, right? And so there's no reason that we can't talk about functions, right? Because my proof is not going to depend on how many dimensions I'm talking about. And you could have a gradient vector in 4 dimensions as well. Or 20, whatever. Let theta be the angle between these 2 vectors. What do we know about angles? This was part of your exam. I had you do one proof on the exam. It had to do with angles. So how do you talk about the angle between 2 vectors? Do you guys know a formula? The dot product, right. So if we dot these two, we can say that, well, grad f dot u has to equal what? That's right. Times the magnitude of u times the cosine of theta. The way I usually write this identity is I write cosine theta equals the dot product divided by magnitude. You guys remember that? Okay. So we kind of took that identity apart here. And now what else do we know? Well, wait a minute. What's the magnitude of u?
1.
Okay. So really all we have is we have the magnitude of the grad f, the gradient of f, times the cosine of theta, right? Now wait a minute. How do you make this as big as you can? Well, cosine, the biggest it can ever be is 1, and that's when theta equals what? 0. So theta equals 0 will maximize our dot product, but the dot product is how you compute the directional derivative. So the whole trick is, if you want steepest descent, right, maximum value of the directional derivative, or ascent, either one, the way to do it is go in the direction of the gradient. So in other words, the gradient in our picture we had before will tell me where the ball's going to roll, right? Because the gradient, it either points upward or downward, depending on whether you positive or negative this thing. But it's going to go that way. And as a matter of fact, how's it going to be related to the level curves then? What do you guys think is the relationship between the gradient and the level curves? Perpendicular, right? And I think if we check, I think that's what your book is going to tell you. So let's just move down to that section. Gradient and level curves. And the proof is going to be very similar, right? It says the line tangent to the level curve is, here's the word they use, what's it called? Orthogonal. Why do we say orthogonal instead of perpendicular? They're warming you up for 4 dimensions. Because I don't have perpendicular anymore, because I can't even draw it. But orthogonal basically means dot product is 0. And actually that's how the proof goes too. So I'm going to skip that because for the sake of time, it's kind of time to move on. I think what's interesting, again, is that the path of steepest descent you can get by computing the gradient. And that's really kind of the point. Okay? Aaron.